Hi, welcome back. We're going to continue with time value of money in chapter 3. Um, and in particular, right now, we're going to start up with projects that have multiple future cash measurements or flows. Um, Most real-world problems involve multiple future cash flows or measurements. So if you want to specialize in two cash flow or two measurement period, two measurement time projects, you're pretty much done with this chapter. But for the rest of us, we're going to have to look at slightly more complicated things, projects that involve a variety of cash flows or times when we want to measure cash in an account. So, for example, let's think about how much would an investor pay now to purchase a bond that is guaranteed to return, unless, of course, the issuer doesn't go bankrupt, 6,000 in 1 year and 8,000 in 2 years. And let's say the interest rate for this deal is 10.4%. So we could start by creating a cash flow diagram for this project. And we'd have to choose whether we want to do a cash flow diagram for the investor, who would be the purchaser of the bond, or the entity selling the bond. So I've chosen here for us the investor, okay, and I've put in on the diagram, which is optional but helpful, that our interest rate here is 10.4%. As always with cash flow diagrams, time is on the x-axis, and the first cash flow here at t equals 0 for the bond purchaser would be the amount they pay to purchase the bond. And the bond contract says whoever is holding this bond in 1 year, they're going to be issued $6,000, and in 2 years, they're going to be issued $8,000, and then the contract is over, so no more cash flows. So CF0 really represents two pieces, okay? It represents a tranche, a piece of that CF0 that's going to grow to 6,000 in 1 year, and another tranche or another piece that's going to grow to 8,000 in 2 years. And the interest rate for each tranche is 10.4%. Okay, so CF0 in this case represents tranche 1 plus tranche 2. Okay, now if we go back to the fundamental time value equation, okay, which we're fairly familiar with, we know that tranche 1 is just the discounted value back to t equals 0 of that $6,000 payment that's guaranteed in a year. And the interest rate for this project is 10.4%. So we'd have tranche 1 is going to be equal to 6,000 divided by 1.104 raised to the 1, because it's being discounted back by 1 year. Similarly, for tranche 2, the value at time t equals 0 of this $8,000 payment is simply the 8,000 discounted back to time t equals 0. So we've got our 8,000 divided by 1.104 again. That's our annual compound interest rate or discount rate for this project, raised to the 2, why 2? Because it's being discounted back by 2 years. And CF0 is just the sum of those two, the 6,000 discounted back by 1 year and the 8,000 discounted back by 2 years. You should check me that if you calculate that out for the 6,000, you get 5.44 thousand, and for the 8,000, you get 6.56 thousand. You add those two up together and you get 12,000. And here, as usual, in this chapter, we're going to use common sense to understand that CF0 is an outflow for the bond purchaser. Okay, a couple things to note about this. First of all, this 12,000 the investor is paying for the bond is comprised of this 5.44 thousand tranche for the 6K to beat this to death, and the 6.5K tranche for the 8K repayment. So CF0, another way to think of it is it's the present value of all the investors' cash flows for this project. So we could call that, and we're going to start calling that, we could call it PV tote for the investor for this project. So in general, we're going to use PV tote or CF0 for these types of projects. Okay, so we'll use one or the other for this type of multiple cash flow project. Okay, so now that we've done that little example and we understand how this works, for a particular example, let's do what we normally do and go ahead and generalize this. So in general, we can say the total PV or PV tote of a set of cash flows that happen in the future is simply the sum of each individual cash flow after it has been individually discounted back to t equal 0. So I want to emphasize that individually discounted cash flow. So now let's be a little pedantic and say we're defining for a set of future cash flows, CF1 happening in a year, et cetera, up to CFN happening at time n. We'll say that PV tote is equal to the total present value of this set of cash flows. And of course, what that means is that's going to be equal to the sum of the individually present valued or discounted cash flows, okay? And mathematically, we could say that's simply PV of cash flow 1 plus PV of cash flow 2, et cetera, plus PV of cash flow n. The key point here is that for each of those future cash flows for this project, for this player or this investor, we have to present value each one first individually before we add them up. That normalizes them all back to t equals 0, so they're on an apples to apples basis. Okay, so now we can use summation notation from mathematics, and we can write a general version of this, which is very nice mathematically, and it's very compact. So using summation notation, PV tote, the total present value for a set of cash flows for this project, is equal to the sum of each individual cash flow, CFI, discounted by 1 plus the interest rate or discount rate for this project, raised to the amount of time in the future that that cash flow happens. And so this sum goes from I equal 1, that's the first future cash flow, to the number of cash flows in the future. And Ti, in each case, is going to be the time of cash flow I, where T is equal to 0 at the time we measure the present value. Okay, this equation is an important equation, 74C. This is another one that you should definitely memorize, write down, be familiar with. This is called the fundamental discounted cash flow equation. Remember we had the fundamental time value equation? This is similar. We're going to use this for cases where we have multiple future cash flows, and we're going to call it the fundamental discounted cash flow equation. Okay, as with our two cash flow problems, we can use, and we already have used CF0 instead of PV tote when it's appropriate. And in this chapter, we're going to use common sense for the algebraic sign of CF0. So, in other words, we can replace 74C up above with this equation, completely equivalent. See, when we're measuring cash flows for one player, one participant, and nothing but her cash flows, we can say her cash flow at time zero, might be an inflow or an outflow, is equal to the sum of all the other cash flows for her in this project, where each one is individually present valued before we add them up. Okay. Another thing to note about 74C, if we go back up here and just think about the algebraic terms in it for a little bit, is that if we are given the future cash flows, so we know all the CFIs, and we know the discount rate R, so we know R, and we know all the CFIs, then clearly we can solve for, without much trouble, we can solve for, where'd my little cursor go here, PV tote or CF0. That's what we did in the first little example we looked at, okay? If we know the PV tote or CF0, we know the interest rate or discount rate, and we know that all the cash flows are uniform, that means that each CFI equals each other CFI, or we could say each one is equal to simply just CF. Then we can pull that CF out of the summation, and we can solve for that pretty easily. Okay, if we know PV tote and we know all of the cash flows, we're not saying they're uniform anymore, we can solve for R. That's going to be difficult, and that's going to be iterative, and we'll think more about that in a little bit in the future. Okay, so let's think about a little bit the deeper meaning of this multiple cash flow formula, the fundamental discounted cash flow equation. Um, in the PV tote form, looks like this. In the CF0 form, looks like this. Notice how we have cash flows on the right side now in either case. And the farther along we go, the more we're going to be interested in just cash flows and not measuring amounts of money that are already in an account and just sitting there. So from a lender's perspective, if we look at the above equation in either form, PV tote or CF0 is the amount we invest now, or the principal we commit now, to receive the future stream of cash flows. And on the other hand, if we have PV tote or CF0 held constant, as our interest rate increases, our future cash flows go up. So that sort of begs the question from a lender's point of view, should we try to maximize our interest rate, well, that's going to be a complicated question that we will discuss more in person. But in general, anytime that you are a lender, you're in a competitive business. So if you raise your interest rates too much, you're going to start losing customers. And another thing that's going to happen is you're going to find the quality customers are going to be offered lower interest rates. So you're going to get stuck with dodgy customers who may go bankrupt and might not be able to pay you back. So that's not good. Okay. All right, so now let's think about this equation from the borrower's perspective here. And from a borrower's perspective, that would be the bond seller in the above little example we were looking at. From the bond seller's perspective or the borrower's perspective, CF0 is the amount the bond seller can get now if she agrees to pay the future stream of cash flows. So in this case, it's maybe good to think about what happens if the future cash flows are constant. Um, and because typically what you do if you are a borrower, you think about how much can I pay back every year without going bankrupt. So, and you set that as a maximum. So that's what your cash flows are going to be here. So if those are held constant, as the interest rate that lenders are going to demand goes up, the amount you get at time t equals 0 goes down. So it's as a borrower, it's in your interest to keep that R as low as possible. Uh, So how do you do that? Well, if you're an individual and you're thinking about a mortgage, you need to have a credit history. We'll talk about that more in person. And you want to have a good credit history. You want to have some credit cards. You have a good record of having paid them down every month, that kind of thing. And if you're an entity, things are very similar, but at large entity scale. You want to be careful that when you have borrowed from your bank in the past, small amounts, that you've paid that back on time, et cetera, et cetera, et cetera. And this is something we'll talk more about in person. Okay. Um, so let's do another example right now. Let's say Velocity Advisors is back in action and they're offering to pay you 6,000 at the end of next year. That would be CF1 for you at what we say EOY1. EOY1 stands for end of year one, okay? And they offer to pay you CF2 of 12,000 at end of year two. That would be 2 years from now. Now is t equals 0 in return for your payment now of CF0. And their interest rate for this deal is 10%. So what am I going to ask us to find from our perspective? Well, we know both the future cash flows, 6,000 and 12,000. We know when they happen, and we know the interest rate is 10%. What's the only thing we don't know, jumping back to our fundamental discounted cash flow formula? We know all the future cash flows, we know the interest rate, we know when they happen. So we're going to want to find CF0 or PV total. Okay. Um, and also, then we're going to want to ask if we have just 15,000 to invest now, can we participate? Okay. So this is going to be very much like the first little example that we did. So first of all, Velocity is saying the total amount we pay now will grow at 10% annually and be repaid in two equal $6,000 payments. Um, sorry about that. I have 12,000 there and I have 6,000 here. And so I'm not gonna say equal. So let me go ahead and correct this for us. Sorry about that. Okay. And I'm gonna say to payments of 6K in 1 year and 12K in 2 years. All right, sorry about that typo. Okay, so what does that mean? It means that if we expand out our fundamental equation here, okay, we have I goes from 1 to 2, okay, CFI equal 1 is 6,000, CFI equal 2 is 12,000. We know our R is 10%. The time of each cash flow is 1 and 2, so I can expand out my summation and give us something that looks like this. The total amount we'd have to cough up now is equal to the present value of that CF1 plus the present value of that CF2, or 6,000 divided by 1.1, that's just raised to the 1 year out, plus 12,000 divided by 1.1 squared. And I'll leave it to you to confirm that that is equal to 15.4 thousand, okay? And as always here, note that this CF0 includes a portion or a tranche corresponding to the first repayment of 6,000 plus a tranche corresponding to the second repayment of 12,000. Okay, just as we saw in our earlier example. Okay, so now I'm going to come back to that in a second. For part B, if we only have 15,000 available, can we participate? No, we can't participate because we would need $15,370 to participate, but we only have 15,000 available, so we would have to say no. All right, so now let me go back to the extra credit portion of this. Notice for this problem, I didn't draw a cash flow statement. A good thing for you to do at home for extra credit would be to draw a cash flow diagram for this project of this form. So this is a cash flow diagram for this project. From the lender's point of view, it's clearly for a different project, okay, where we have 3 annual payments of 50,000 coming back to us, okay. But the thing that is important here is that it shows that this total CF0 here equals CF0 equals, we could also call it PV tote. The nice thing, the thing I really like about this cash flow diagram is that it shows for the total present value or cash flow 0 that we would have to invest now in this project to enjoy these future 50,000 cash flows. It shows each tranche and how each tranche is obtained at t equals 0 by discounting back the future value of each tranche. So I think it would be a good thing, probably something you'll see on homework, probably something you'll see on exams, for you to be able to create a cash flow statement like this for this project. So you would have, instead of 50 up here, you'd have 6K for this one, and you would have 12K for this one, and nothing else. You don't have a third cash flow in this case, and etc. I'm not going to solve the whole thing for you, but again, that would be a good thing to know about. Okay, so let's do another example. Lots of examples here. Really important to be comfortable with this stuff. Zero Motorcycle Street Fighter S is available at Amazon for $9,000. Zero Motorcycles is probably the best electric motorcycle maker in the country these days. You can check them out on the web. They have some really, really interesting motorcycles. Rent-A-Center is also offering the same bike for 0 down and 2 uniform annual payments of 6,000 starting a year from now. your bank gives you 10% annual interest on your savings account. So Rent-A-Center is a real company, and it is in the business of giving you stuff that you pay for over time, more or less exactly like what we've just described here. So what I'd like us to find is, should we buy the bike from Amazon or Rent-A-Center? Why? Okay, and let's assume for the Rent-A-Center option that we would invest enough now in our savings account to make two future payments. So this is sort of similar to the trust fund issue with your parents, except we are putting enough aside now to make two payments in the future, not one. All right, so let's see how this shakes out. So for us, the participant is going to be you or me or us together, however you want to think about it. And we're looking at two projects. The Amazon project is simply expend CF0, comma Amazon now of 9,000 and get the bike. Okay, so that would be a negative cash flow of 9,000, and in return we get the motorcycle. Okay, the project we want to compare that to is the Rent-A-Center project. Okay, and in that project we have CF1 equals CF2 equals 6,000. Remember, the deal with Rent-A-Center is we get the bike now, and a year from now we pay them 6,000, and then in 2 years we pay them another 6,000. Okay, um, and so what we'd want to do for the Rent-A-Center project is we want to put an amount in the bank now, which will be PV tote or CF0, that is large enough so that one piece of that will grow to 6,000 in 1 year, and another piece of that will grow to 6,000 in 2 years. Okay, so formally we could say that for the Rent-A-Center project, PV tote equals CF0 comma rack for Rent-A-Center, the amount we would put into the bank now, and that's going to grow at 6%. Okay, and in either case, whether we're saying PV tote or CF0 comma rack, what is that PV tote equal to? Well, it's simply equal to the one payment we've got to make discounted back by 10% by 1 year, plus the second payment we've got to make discounted back by 2 years. Okay, and I'll leave it to you to work that out. If you work that out, you get 10,000. Okay, and so what's our conclusion? Well, if we go with the Amazon deal, we pay 9,000 right now, okay, and then we're done. If we go with the rack deal, okay, we present value those. We're saying what's the equivalent value of both of those tranches evaluated now at t equal to 0, or how much do I have to put aside now at t equals 0 in my 10% guaranteed account to get my 6,000 in a year and another 6,000 in 2 years? The answer to that, and that happens at t equals 0, is we would have to put 10,000 aside right now. 10,000, putting that aside right now, is clearly more than 9,000 paying that to Amazon right now. So clearly the Amazon deal is best. Also, good to note here, interesting to note that if we go with the Amazon deal, you could think of this as, well, we'd also have 1,000 left over. So we could put aside additionally 1,000 and let that grow at 10% for 2 years, and we'd have a bigger pile than 1,000 at the end of the 2 years. So that would be nice too. Okay. All right, so now I want to go a little bit more into why, when we're solving for R with multiple cash flow problems, this is difficult. Um, so let me get right into that. So here's our fundamental discounting equation. And remember, if we know the future cash flows, the interest rate or discount rate, we can solve for the PV tote. We've done that 3 times now, so that should be very familiar. If we know the PV tote, the R, the uniform cash flows, we'll show ourselves very soon that we can solve for what these uniform cash flows are. And if we know the initial amount we have to throw into a project, PV tote or CF0, and we know what the future cash flows are, we can solve. The only unknown in this equation then is R, but this is difficult to solve for, and let's see why. Let's consider a case like this, okay, where we know PV tote, okay, PV tote is equal to 10, okay? And we also know our future cash flows when they happen. So our first future cash flow is 6 and it happens in 1 year. So we would discount that back by 1 year, okay, to get everything to add up to 10 at t equals 0. And our second future cash flow happening in 2 years is 8, okay, and so we would want to discount that back by 2 years with our compound annual interest rate R. So you can see in this equation clearly the only thing that we don't know is R. So we could multiply both sides of this equation by the quantity 1 plus R squared, and that would give us this equation here 10 times after a little bit of algebraic manipulation. So multiply both sides by 1 plus R squared, and then rearrange terms so the right-hand side just has 0 on it, and we get an equation looking like this. 10 times 1 plus R squared minus 6 times 1 plus R minus 8 equals 0. And if that makes your skin crawl a little bit, it probably should, because I'm bringing you back to high school algebra, where we had equations like this, which represented finding the roots of a parabola or a quadratic equation. And again, bring you back to high school algebra. Equations like this always have 2 roots. They may have 2 real roots. One might be a complex number. Sometimes they'll have a double root, so we still get 2 roots. They happen to be the same number. Um, and sometimes one of the roots is a real but negative number. Eek! Okay, so this is really trouble. So we have 2 roots. If we have 2 positive real number roots, which is the correct one, we can't just willy-nilly say it's the smallest one. What if we get 1 positive real root, 1 negative real root? Can we say anything about which one is the right root? Not necessarily. And also, I picked here the easiest little problem I could for us, okay, finding the roots of a quadratic, okay. But what if the I was equal to 3? What if we had PV tote equal 10 equal this term plus another term where the cash flow happened in 3 years? Then I'd have to multiply both sides by 1 plus R cubed, and I would be finding the roots of a third order polynomial. Also, what if the timing of these cash flows was not integer years? We've done nothing that says the timing of our future cash flows has to happen at the end of a year. Cash flows happen whenever they happen in a project, okay? So if the times of these future cash flows is not at the end of a year, then we're going to have an exponent here, which is a real number, and then to solve this, we're going to be finding the roots of what's called a real equation, and that is truly difficult stuff. Um, so That is a problem, and we're going to come back to that. Right now, I just want you to know that that's a big problem, and later we're going to come back to this one final time to talk about when we can make some conclusions about this and solve for some R's that we trust and when we can't. All right, so before we do that, I'd like to walk us through some constant cash flow projects. And these are projects where right now, at t equals 0, we're going to have to make a payment in return for a uniform set of cash flows in the future. In other words, all of the cash flows in the future are equal to each other. Something like this. And so here we could say equals F, or we could just say equal. To use our terminology, we could say CF. Okay. Now, also, of course, this could be, we're looking at this from the perspective of a lender or a borrower. Hint, hint, hint. Okay, it's lender because the money goes out in the beginning. We could look at something like this from the perspective of a borrower, where we'd have one positive cash flow here, and then all the rest would be negative cash flows. So that would be something like your parents getting a mortgage loan. They get a big blob of money to help them buy a house, and in return, they pay every month. There's a negative cash flow going out for the next 30 years, that type of thing. So we can look at them from the point of view of lender, borrower, but the key thing is, in all cases, the future cash flows are all constant. F1 F equals F2 equals Fn equals F, or in our terminology, just CF. So what types of loans are these? Like I just said, mortgage, car loans work this way, annuities work this way, annuities do work this way, and etc. And that's going to be what we're going to be looking at in detail in the next video in this sequence. So until then, I'm going to say sayonara.